Welcome to Theory of Computation. This is lecture number 2. In the first lecture, we heard an informal story of computation and we discussed what kind of questions we'll be answering in this course and will be asking in this course. As you know, this is a very interesting course. However, in order to answer these questions, now we have to get into the details, the nitty-gritty of this subject. So in order to do that, we have to get more technical. So today's lecture is going to be quite technical, and today we will start by reviewing some basic definitions from automata theory. After that, we will define Turing machines. As I had told you in the first lecture, Turing machines is a very, very important concept in computer science. In fact, for us, it is the most important concept. And the rest of this course is going to be a study of the Turing machines. After that, we will look at some simple examples of Turing machines and try to get a grip on how these machines do perform their computations. Let us start by recalling some very basic definitions from automata theory. Let's start with the concept of an alphabet. What is an alphabet? Well, for us, an alphabet is going to be a finite set. Any finite set would do. For example, computer scientists like working with the alphabet that consists of only two elements, 0 and 1. The elements of the alphabets are usually called symbols. So, the favorite alphabet for computer scientists is the one that consists of two symbols, namely 0 and 1. We can have other kinds of alphabets. For example, here sigma 2 is an alphabet that consists of all the lowercase letters in the English alphabet. We are very familiar with it. It consists of 26 symbols. Another alphabet that's shown on the slide right here consists of 5 symbols, namely 0, 1, X, Y, and Z. As you can see, there is no restriction on what kind of symbols there would be in an alphabet. For us, an alphabet is just going to be a finite set of symbols. Starting with an alphabet, we will start making more complex things. For example, the first important concept is that of a string. Let us start with an alphabet sigma, and if we take a finite sequence of symbol over this alphabet, that is called a string. Remember, whenever you talk about a string, you must have an alphabet in mind. So for example, if your alphabet consists of 0, 1, then 0, 1, 0, 0, 1, 0, 0 is a string over this alphabet. Let us look at another string, which is a string over the second alphabet that we saw that consisted of the first 26 letters in the English alphabet. This string is AB, RA, CA, DA, BRA. You can read this if you want. It says abracadabra. This is a string over the alphabet sigma 2. The number of symbols contained in a string is called the length of the string, and it is denoted by placing 2 bars around the string. So for example, there is a string which contains no symbol. It's a very special string, and we will denote this string by the symbol epsilon. In some books, it's also denoted by lambda. Notice that this string has length 0. It is called the empty string. You can imagine the empty string by saying that you wrote nothing. Let us look at some other strings. For example, 0, 1, 0, 1, 1 is a string of length 5 over the alphabet 0, 1. The empty string is also a string of length 0 over the same alphabet. 1, 0, XX is a string of length 4 over the alphabet sigma 2, which consists of 4 symbols 0, 1, X, and Y. AB, PQ, RS, XY is a string of length 8 over the alphabet sigma 3, which consists of the 26 letters of the English alphabet. Notice that it is not necessary that each symbol in the alphabet must occur in a string. A string can just be repeated, one particular symbol repeated several times, or it can be any combination of these symbols. Another thing to notice about strings is that it is an ordered sequence. There is a concept of the first character, followed by the second character, followed by the third character, and so on. So for example, if we look at the string 01011, 0 is the first character or first symbol in the string. 1 is the second symbol in this string. Once again, 0 is the third symbol in this string. 1 is the fourth symbol in this string. And finally, 1 is the fifth symbol in the string. This string consists of only 5 characters. One very important thing to remember about strings is that they all have finite length. So, we start with the concept of an alphabet, which is just a finite set. And using the elements of this set, we make strings. Strings is a very simple concept. It's like in a language, when you learn a language, the first thing you learn about the language is the alphabet. And after that, once you have learned the alphabet, you put the symbols of the alphabet or characters of the alphabet or the letters together in order to get words. Similarly, in this subject, we will start with a finite set, which we will call our alphabet. And by putting these characters together in a sequence, we will make what we should call words, but there's a more technical name for it. We will call them strings. Suppose that you have a string x, which is equal to x1, x2, x3, and so on up to xn. So this string consists of n symbols. It's a string of length n, and the first symbol is x1. The second symbol in the string is x2. The third symbol in the string is x3, all the way up to the nth symbol, which is xn. This is a string of length n, and let's say you have another string y of length m. So y is equal to y1, followed by y2, followed by y3, all the way up to yn. This is a string of length m. Then we define what we call the concatenation of these two strings x and y, which is usually written as xy. This is the string obtained by appending y to the end of x. Thus, xy equals x1 followed by x2 all the way up to xn, and then followed by y1 followed by y2 all the way up to yn. Concatenation is a very, very simple concept. Suppose you have a string x and you have another string y. When you take the first string x and then write y after it, you have concatenated the two strings. So it's a very, very simple concept. Let's look at some examples. Let us say that you have a string 01 and you have a string 10. What is the concatenation of these two strings? It's simply obtained by taking the first string 01 and then writing 10 after it. Therefore, the concatenation of these two strings is going to be 0110. Let us look at another example. Let's take the string 111 and let us take the empty string and let us concatenate the two strings. Well, what would be the result? Well, the result would be 111 followed by the empty string. But the empty string contains no characters. So the concatenation of 1, 1, 1 and the empty string is just 1, 1, 1. In fact, the concatenation of any string with the empty string gives you the original string back. This is because the empty string does not add characters. Let us look at another example. What would be the concatenation of 10xx and 00yy? Well, it's simply 10xx00yy. So, you can see that concatenation is an extremely simple concept. What you do is you take the first string and write the second string after it, and what you have is the concatenation of two strings. It's a very simple concept, but we would like to define it properly. The concatenation of the empty string with the string ABC is just the string ABC. So the empty string is a very interesting string. When it is concatenated with any string, whether the empty string comes first or later, it doesn't matter. You get the second string back. In other words, the concatenation of the empty string with X is going to be X, and the concatenation of X and the empty string is also going to be X. If you have a string X and a string Y, suppose the string X has length N and the string Y has length M, what would be the length of the concatenation of X and Y? Well, it's going to be the sum of the lengths of the two strings. Therefore, we have the following simple formula. The length of XY is equal to the length of X plus the length of Y. We can simply remember this by saying that the length of the concatenation of two strings is the sum of their lengths. Let X be a string. We will let X to the power K denote the concatenation of X with itself K times. So, for example, if X is equal to 0, 1, 0, 1, 1, then 0, 1, 0, 1, 1 to the power 3 is just 0, 1, 0, 1, 1 repeated 3 times. In particular, 0, 1, 0, 1, 1 to the power 3 is equal to 0, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, 1. Well, what would be if I take the empty string and raise it to the power 5? That would be like writing the empty string 5 times. But the empty string consists of no symbols, so I'm writing nothing 5 times, so I get the empty string back. Similarly, if I take 1, the string 1, which consists of only one symbol 1, and raise it to the 10th power, I will get 1 repeated 10 times. In the last example, we have the string ABC, which is raised to the 4th power. And the answer, of course, for that is that it's ABC, 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 ABC. That is, ABC repeated 4 times. Notice that we are treating these symbols as symbols. They have no other meaning. They are not numbers. Even though the alphabet consists of 0 and 1, we are not thinking of 0 and 1 as numbers, but as two distinct symbols. And the operation of concatenation does not look at the meaning of these symbols. It simply puts one string after another. If we have a string which consists of some zeros and ones, and we raise it to the 50th power, we simply take the string and repeat it 50 times. We are not looking at any meaning or any arithmetic meaning or any other meaning in these symbols. Strings are just abstract objects. They are formed by taking symbols of an alphabet and writing them down in a sequence. Let us go further. Suppose we have two sets of strings. So now, instead of a single string, I have a set A which can have one or more strings in it. And suppose I have another set B of strings. We define AB to be the concatenation of all strings such that the first string comes from A and the second string comes from B. For example, if A consists of 0, 0 and 1, 1, and B consists of X and Y, then AB will consist of 0, 0, X, 0, 0, Y, 1, 1, X, and 1, 1, Y. Notice that I have taken every string of A and every string of B and concatenated them and put them in my set AB. Another example is when the set A consists of 1, 0 and 0, 1, and the set B consists of X, X, Y, and XY. In this case, notice that B has 3 strings, but they're not all of the same length. There are 2 strings of length 2 and 1 string of length 1 in it. In this case, the set AB will be equal to 10XX, 10Y, 10XY, 01XX, 01Y, 01XY. Once again, you'll notice that I've taken every string in the set A and concatenated with every string in the set B to obtain AB. Of course, as you would have guessed, the size of the set AB is going to be the product of the sizes of A and B. Notice that the size of a set of strings is the number of strings that are in the set, not the lengths of the strings that are in the set. A set can have many strings of different lengths, but the size of a set of strings is the number of strings that are in the set, not the lengths. Let us look at another set A of strings. We define the set A to the 0 to be the set consisting of the empty alphabet. And we define the set A to the K to be the product of the set A to the K minus 1 and A. So, A to the K consists of taking K strings from A and concatenating them together. Let us look at an example. Let us say that A is 00, 11. Then A to the power 2 is going to be the set of strings which consists of 0000, 0011, 1100, and 1111. If the set A consists of A and B, then A to the power 2 is going to be AA, AB, BA, and BB. If we take the same set and raise it to the third power, we'll get all strings of length 3 over AB. Namely, we will get AAA, AAB, ABA, ABB, BAA, BAB, BBA, and BBB. Of course, the size of A to the power K is going to be the size of the set A raised to the power K. Let us take an alphabet sigma. Then sigma to the K is going to be the set of all strings of length K over this alphabet. So for example, if sigma is equal to A, B, C, D up to Z, namely the English characters, then sigma to the 7 is the set of all possible strings of length 7 I can make out of these characters or out of these symbols. If I have alphabet sigma, then sigma to the K consists of all strings of length K over that alphabet. Sigma to the 0 will consist of all strings of length 0 over that alphabet. The only string of length 0 that we know of is the empty string. So sigma to the 0 just consists of a single element, the empty string. Sigma to the 1 will consist of all the symbols. Sigma to the 2 will consist of all strings of length 2 over the alphabet. Sigma to the 3 similarly will consist of all symbols of length 3 over this alphabet. Next, we come to a very interesting concept. We will let sigma star denote the union of all these sigma k's. So sigma star is the set of all strings over the alphabet sigma. Formally, sigma star is the union of sigma to the 0, sigma 1, sigma to the 2, sigma to the 3, and so on. This set consists of all strings over the alphabet. So if sigma is the alphabet 0, 1, then 0, 1 star denotes the set of all strings that I can write using the symbols 0 and 1. Examples of strings in 0 to the 1 star are the empty string 1 0 1 0 0 0 1 1, and the last example, which is an extremely long string over this alphabet 0 1, too long for me to read right now. So if sigma is an alphabet, sigma star denotes the set of all strings over the alphabet. So if we take the alphabet 0 1, then what are the things that are in sigma star? Well, anything that you can write with zeros and ones. So start writing zeros and ones, and when you finish, you will have a string which will be in sigma star. Of course, sigma star consists of infinitely many strings. But what is important to remember is that every string in sigma star itself has a finite length. So sigma star is an infinite set. However, every string in sigma star has finite length. Let's now talk about lexicographical ordering of strings. So we are going to order the strings in sigma star using a dictionary order, except for in this order, the shortest strings are going to precede the longest string. Thus, to write the strings of 0, 1 star in a lexicographical order, we first write all the strings of length 0 in dictionary order, then all the strings of length 1 in dictionary order, and so on. Thus, the lexicographical ordering of 0, 1 star is the empty string 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 0, 0, 1, and so on. There is a very nice and simple way to get the lexicographical ordering. It's very neat, and it's very easy for computer scientists to understand as they know how to write numbers in binary. Let us first write down all the integers that we know of, 1, 2, 3, 4, 5, 6, and then convert them into binary, and we get this sequence of strings 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and so on. Now let us throw away the leading one from each one of these strings, and we get all the strings in lexicographical order as follows. We get the empty string first, then 0, then 1, then 0, 0, then 0, 1, and 1, 0. Now we are going to start studying another very important concept, and that is the concept of a language. A language is just going to be a subset of sigma star. Let us look at 3 examples. The first example is the language L1, which consists of the following strings: epsilon, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 0, 1. L1 is a finite language. Let's look at another interesting language, which is infinite. L2, which is the set of all strings over 0, 1, which start with a 0. So L2 consists of all the strings which start with a 0, and it does not consist of any string that starts with a 1. The language L3 is the set of all strings that end with a 1. Let's note that 1, 0, 0, 0, 1 is in L1, but 0, 0, 0 is not in L1. Similarly, the strings 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1 are strings in L2, and 1, 0, 1, 1, 1, 1, 1, 1, 0, 0 are not in L2. 1, 1, 1, 1, 0, 0, 1 are strings in L3, and 0, 1, 0, 1, 0, 0 are not strings in L3. 0, 1, 1 is a string that is present in all these languages. Let us look at a more complicated language over 0, 1 star. Let LP be the set of all strings such that when we interpret this string in binary, we get a prime number. So for example, 1, 1 is a string in LP. 1, 0, 1 is also a string in LP because it denotes the number 5, which is a prime number. Similarly, 1, 0, 0, 0, 1 is also in LP because it denotes the number 17, which is a prime. However, 1, 0, 0, which denotes 4, is not in this language, as this language only consists of primes. If I give you a string, it is not at all easy to tell whether that string belongs to the language LP. What you will have to do is take that string, which is a binary string consisting of zeros and ones, convert it into a number, and check whether that number is a prime number or not. That is a complicated procedure. However, this language is well defined, and it is a language over the alphabet 0, 1. The fundamental problem that we are going to deal with in this course is going to be as follows. We will be given a language, And what we would want to know is whether a string belongs to this language or not. For example, that language may be LP, which is the set of all strings which represent prime numbers. We would like to know if a string represents a prime number. What we would want to do is build a machine to which we can give this string as an input. And the machine performs a computation, and then instead of us having to do the computation, the machine will perform a computation and eventually tell us whether that string belongs to the language or not. So for example, we would like to build a machine in which if we give a binary string, it would tell us whether that binary string represents a prime number or not. This is going to be the fundamental goal. And the machines that would perform this task for us are going to be Turing machines. What we want to do right now is just discuss machines which will provide us yes-no answers. So we will have a language, and the machine will tell us whether the string belongs to the language or not. Let us first discuss informally what a Turing machine is. A Turing machine is going to consist of an input tape on which we will write a string. The Turing machine will then have a read-write head with which it will read the input and write some symbols on the tape. This is how a Turing machine will perform its computation. It will read what is written on the tape and decide to write something, move left or right, or change its state. It will continue to do that for a little while, and after a little while, it will either accept or reject that string, thereby telling us if the string belongs to the language or not. A Turing machine has an input tape which is infinite, hence the machine has unlimited memory. It has a read-write tape head which can move left and right and change symbols while the machine is performing its computation. The tape initially is blank everywhere. We write an input on the tape and turn the machine on by putting it in a designated start state. The machine starts a computation and may eventually produce an output. The output can be either accept or reject. The machine produces this output by going into two designated states which are labeled accept state and the reject state. Let us be a little more formal with this definition of a Turing machine. To formally specify what a Turing machine is, we have to specify 7 things in total. Namely, first of all, we have to tell what are the states of this Turing machine. The second thing to specify is the input alphabet. The alphabet which the user is allowed to use when he or she is giving an input to this Turing machine. The third thing we need to specify is what is called the work alphabet, the symbols that the Turing machine is allowed to write on the tape. Other than that, we also have to specify a start state and 2 states which are designated as the accept and reject state. And lastly, and most importantly, we have to specify how the machine will perform its computation. This is called the transition function. Let us look at the formal definition of a Turing machine. Formally, a Turing machine M is going to be a 7-tuple Q, sigma, gamma, delta, Q naught, QA, and QR, where Q, sigma, and gamma are all going to be finite sets. Q is going to be the set of states of this Turing machine. Sigma is the input alphabet, and this alphabet is not allowed to contain a special symbol which is called the blank. The work alphabet is going to be a superset of the input alphabet, and it will contain this special symbol called the blank. Q naught is going to be the start state. QA is going to be the accept state of this Turing machine. QR is going to be the reject state. Lastly, delta, which actually tells us how this Turing machine works, is going to be a function from Q cross gamma to Q cross gamma cross LR. This is called the transition function. Let us discuss these 7 things one by one. The tape is initially empty. The user can write an input only using the symbols of the input alphabet sigma on the tape. The rest of the tape is left blank. Hence, blank is not allowed to be in sigma. The user is not allowed to write a blank. He or she can use any symbol in the input alphabet and write it consecutive symbols on the tape, and the rest of the tape cells are left blank. Q is the set of states that this machine can be. Gamma is the set of symbols that this machine is allowed to write. Q0 is going to be the start state of the machine. Each time the machine performs a computation, it starts from the start state. QA is the accept state. When the machine enters QA, it declares that it has accepted the input. QR is the reject state. When a machine enters QR, it declares that it has rejected the input. Delta, which is the most important part of the Turing machine, is the transition function. It actually describes how the machine will perform its computation. How does a Turing machine work? We have to understand how it takes a single step. The transition function delta tells us how it takes a single step. The Turing machine looks at the current symbol under its tape head and the state that is in, and depending on this, it decides the following 3 things. 1. What will be the next state? 2. What will it replace the current symbol that it's scanning with? 3. Whether it'll move its head left or right. This is why the transition function has Q cross gamma as its domain, which means the transition function actually needs to know what's the state and what's being read by the tape head. And it tells us what the machine should do in all these possible situations. The range of the transition function is Q cross gamma cross L comma R, which means that it would tell us what would be the next state, what would be the replacement of the current symbol, and whether the tape head will move left or right. Therefore, the delta function specifies all the 3 decisions the machine has to make, and it does so by looking at the current state and what is being read by the tape head currently. Let us look at a very simple Turing machine, M1. In order to describe a Turing machine, I will have to specify all 7 things. This machine has 3 states. Thus, Q is equal to Q0, QA, QR. The input alphabet for this Turing machine is going to be 0, 1. The work alphabet for this Turing machine is going to be 0, 1 and the blank symbol. This is a very simple machine. The start state is going to be Q0. The accept state is going to be QA. The reject state is going to be QR. And the transition function delta is given as follows. The transition function can be given by what we call a transition table. So let us read this transition table. The first row of this transition table has Q0, 0, QA, 0, R. What does this mean? This means that if the machine is in state Q0 and it reads the symbol 0, its next state would be QA and it would replace that symbol by 0 and move to the right. The next row of this transition function is Q0, 1, QR, 1, R. This means if the machine is in the state Q0 and it reads the symbol 1, it will go into the state QR, replace the current symbol with 1, and then move right. The third row of this table has Q0 blank, QR blank, R in it. This means if the machine is in the state Q0 and it reads a blank, it would move into the state QR, it would replace the blank with a blank and move to the right. As you can see, the rest of the entries in this table are not filled. That is because QA and QR are accept and reject states. Once the machine reaches these states, the computation of the Turing machine stops or halts. After that, the machine does not compute anymore. It has actually produced an output. Therefore, I have not specified these entries. This is because they are completely irrelevant. I could fill them with anything I want, and that would have no bearing on the workings of this Turing machines. Let us look at what this Turing machine would do if we give it various inputs. Let us suppose that this Turing machine is given a blank as an input. So the user does not give it any input. So the input is epsilon, the empty string. In that case, the machine starts in the state Q0 and it reads a blank. According to the transition function, it should go into the state QR, replace the blank with a blank and move right. Well, what does that mean? That means the machine has actually rejected the empty string. So the machine has declared the empty string as rejected. Let us suppose we give this Turing machine 0 as an input. It starts in the state Q0, reads the 0, and according to the transition function, it has to go into the state QA, replace it with a 0, and move to the right. Hence, it goes into the state QA and accepts this input. So this machine accepts the string that consists of the symbol 0. Let us suppose that the input is 1. Then the machine starts in Q0. It reads the first symbol on the tape, which is a 1. And since the transition function says that if the machine is in state Q0 and reads a 1, it should go into the state QR, write a 1, and move to the right. Hence, the Turing machine will go into the state QR and reject this input. So this machine rejects the input 1. This Turing machine will accept all the strings that start with a 0. Since from the start state it goes to either the accept state or the reject state, hence only the first symbol of the input will be read and the input would be accepted or rejected. And it's simple to see that if the first symbol is 0, then the input would be accepted, and if the first symbol is not 0, then the input would be rejected. So our first example of a Turing machine was very simple. The machine only consisted of 3 states. It wasn't doing anything terribly interesting. It was just looking at the input's first character and checking if it was 0. If the character was 0, if the first symbol of the string was 0, it was accepting the input, otherwise it was rejecting. Of course, this Turing machine was very simple and it wasn't doing anything that we ourselves could not do. But Turing machines can be much more complicated. Let us look at a more complicated example now. I want to now describe a Turing machine M2. So once again, I have to specify all 7 things. First of all, I have to tell you what are the states of this Turing machine. I have to tell you the set of states Q, which is in this case Q0, Q1, Q2, Q accept, and Q reject. So this Turing machine has 5 states. Once again, I have to specify the input alphabet, which is going to be 0, 1 in this case again. The work alphabet is just as before. It is 0, 1, and the blank. The start state is Q0, QA is the accept state, QR is the reject state, and lastly, I have to describe to you the transition function of this Turing machine. Let us look at the transition function, which is given by the following table. If the machine is in state Q0 and it's reading a 0 or a 1, then it moves into the state Q1 and it does not change the symbol that it's reading and it moves to the right. If the machine is in state Q0 and reads a blank, it goes into the reject state and moves to the right. If the machine is in Q1 and it reads a 0 or 1, it does not change the symbol and moves to the right and stays in the state Q1. If the machine is in the state Q1 and it reads a blank, it goes to the state Q2, does not change the blank, but this time the machine moves to the left. If the machine is in state Q2 and it reads a 0, then this machine goes to the reject state. if the machine is in state Q2 and reads a 1, then it goes to the accept state. Once again, I have not specified what this machine does when it reaches the state QA or QR. That's because QA and QR are halting states, and after that, the machine will not compute anything. Let us see what this machine would do if we were to give it the empty state as an input. Well, the transition function says that it would immediately reject the empty string. Suppose the input is 0, then the machine starts in the state Q0, it reads the first symbol, which is 0, and goes to the state Q1 and moves to the right. Once it's in the state Q1, it reads the current symbol, which is blank, and moves to the left and goes into the state Q2. Now, the machine is reading 0 again, but is in the state Q2. Since delta of Q2, 0 is QR, the machine rejects this input. Let's look at what happens next. For example, what would happen if I were to give this machine the input 1? Then the machine will start from the state Q0, go into Q1 and move to the right. In the next state, the machine will be in Q1. It will read the blank symbol and move to the left and go into the state Q2. When the machine is in state Q2 and reading a 1, then the machine accepts the input. This way of working seems to be very tedious. So let us work out a better way of following a computation of a Turing machine. This brings us to the next concept. Now we will describe what a configuration of a Turing machine is. Intuitively, at any point, a Turing machine has some contents on its tape and it's reading a particular input. That is what a configuration of a Turing machine is. A configuration of a Turing machine describes completely what's written on the tape and where the tape head is and what is the current state of the Turing machine. Let us look at what will happen if we were to give 00101 as an input to the machine M2. We can represent its initial configuration with Q0 00101. This means the machine is in state Q0. It is reading the symbol that is the first to the left of Q0. The tape contents are 00101. Well, from this configuration, since the machine is reading a 0, it will go into the state Q1 and move to the right. We can represent this by writing 0 followed by Q1 followed by 0101. This means that the machine is in the state Q1 and it is reading a 0. The tape contents can be easily found out by ignoring the state in the configuration. Once again, we see the delta of Q1, 0 is Q1, 0R. That means the machine will keep moving to the right without changing any of the symbols. When the machine is in the state Q1, it will stay in the state Q1 and not change any symbols and keep moving to the right as long as it does not find a blank. This is because delta of Q1, 0 is equal to Q1, 0, R, which means if you see a 0, replace it with a 0, don't change it, and move to the right. Similarly, delta of Q1, 1 is equal to Q1, 1, R, which means if you see a 1, replace the 1 with a 1, don't change it, and move to the right, and stay in the state Q1. So, once the machine is in state Q1, it will keep moving to the right without changing the contents of the tape till it reaches a blank. So this Turing machine will finally reach the following configuration, which is 00101 Q1. At this point, the tape head is reading a blank. Now we look up the transition function and observe the delta of Q1, blank is Q2, blank, left. So now the machine will change its state to Q2 and move to the left. At this point now, the machine goes in the configuration 0010 Q21. And since delta of q2 comma 1 is equal to qa comma 1 comma r, the machine will eventually reach 00101 qa and accept this string. Can you tell me what are the strings that are accepted by this Turing machine and which are the strings that will be rejected? Well, if you think about it for a moment, this Turing machine will accept all strings that end with a 1 and reject all strings that do not end with a 1. In particular, it will reject the empty string. Well, today we have looked at what Turing machines are, we've formally defined them, we have looked at a couple of examples, and we have also stated what a configuration is for a Turing machine. In the next lecture, we would formally define what a configuration of a Turing machine is and what a computation is. And that would get us started on what we want to do. Thank you. I would see you next time. Goodbye.